In this problem, a manager realizes that he needs to step up production for a while, so he or she's considering hiring some half-time employees. But the manager is wondering, are these half-time employees going to work out? Will they be as productive? Is this a good way to do this? Or he might be afraid. He might also think, well, maybe half-time employees might even be more productive because they're only working a half day and they're not going to be as tired. So he decides to do a test measuring the production rate of half-time employees and full-time employees. And so these two sets of employees are different. So we're going to be doing an independent sample or a two-sample comparison, and we want to compare the production of the half-timers. Oops, I spelled half-timers wrong. Half-timers with full-timers. And so what we want to do is we want to start off with our hypothesis. And we're just going to hypothesize that they're different. The productivity of half-timers and full-timers will be different. This is a two-tailed test, two-tailed hypothesis, and of course we're going to use alpha equals 0.05, which we always use unless we specify it. And the test that we're going to use is going to be a t-test, because we want to compare the averages between two means, two sample or independent sample, assuming equal variances. So that's a type of test that we're going to use with data analysis. So let's go to data analysis. We're going to use a t-test, two sample, assuming equal variances. And our first variable is going to be the half-timers. The second variable, let's delete what was there, is going to be the full-timers. The hypothesized mean difference is 0. We've got labels for the output range. Let's put it here in H7, and we press OK. And let's round off the numbers to number format. Let's make this wider so we can tell what's going on. And let's see, what do we have? So we have the mean is 32.33 for half-timers versus 29.67 for full-timers. So the half-timers in the sample are more productive. Now we want to know if this is significant. If it's significant, that means that we can make that conclusion for all of the workers in this family or this factory, all the half-timers and all the full-timers. This is just a sample of them. So we had 6 of each. That's important to note. And the degrees of freedom in this test were 10. That was the 2n minus the two averages we calculated. And we made a two-tailed hypothesis. So the t-stat is 0.6. And the p for the two-tailed test is 0.56. That's really high. In fact, that's kind of like what you would expect if there was no difference between the half-timers and the full-timers. So we can conclude that the productivity of half-timers, and we put mean equals 32.33, n equals 6, was not significantly different than the productivity of full-timers, and we have a mean of 29.67, n equals 6. And now we can report our t statistics here. So we're going to put control I, T, control I, then parentheses, we put the degrees of freedom, close parentheses, space equals 0.60. And then we do comma, and then we're going to put our p-value in italics, control I, P, control I, space equals 0.562 tails. Now this is kind of surprising because you can see that, yeah, it looks like the half timers were 10% more productive, but that's because we have such a small number and there's a big variety of how productive the different workers are, that we would expect a big variety between such a small sample. Now, if we had a larger sample, we might be able to detect a difference, but we can't tell if it was going to be positive or negative because there's just so much natural variation. So we'd have to have a much larger sample to detect these differences.